Welcome! In this session, we'll explore LeetCode problem number 1925, count squaresome triples. It's an interesting mathematical problem that involves finding all Pythagorean triples within a given range. Let's dive in and break this problem down step by step. This problem is called count squaresome triples, and the goal is to determine how many squaresome triples exist for a given integer n. A squaresome triple is a set of three integers, a, b, and c, such that a(2 plus b squared equals c(2), where all three numbers fall within the range of 1 to n. For example, if a is 3, b is 4, and c is 5, they form a squaresome triple because 3 squared plus 4 squared equals 5 squared. The input to the problem is a single integer n, which has a value between 1 and 250. The output will be a single integer that represents the count of all such valid triples, a, b, c, within the range. Now, let's look at some examples to better understand how this works. In the first example, the input is n equals 5. The output is 2, because there are exactly two squaresome triples for this case. The first triple is 3, 4, 5, where 3 squared plus 4 squared equals 5 squared. The second triple is 4, 3, 5. Notice that the order of a and b matters, so these are considered distinct triples. This demonstrates how the problem evaluates all valid combinations of a, b, and c within the given range. Next, we can look at a larger example to see how the number of triples increases. In the second example, the input is n equals 10. The output is 4, because there are 4 valid squaresome triples. The first two are the same as in the previous example, 3, 4, 5, and 4, 3, 5. Additionally, at this larger range, we now have 6, 8, 10, since 6 squared plus 8 squared equals 10 squared, and 8, 6, 10, which is the reverse of the previous pair. The constraints specify that n can go up to 250, so the number of triples grows as n increases. However, if n is very small, such as 1 or 2, there are no valid triples because the sum c(2) cannot be formed. This means the output in those cases would simply be 0. To solve the problem of counting squaresome triples, we start by understanding the core task, finding triples, a, b, and c, such that a superscript 2 plus b superscript 2 equals c superscript 2, with all three values between 1 and n. The brute force approach is the most straightforward method. Here, we iterate through all possible combinations of a, b, and c within the range, 1, n. For each combination, we calculate a superscript 2 plus b superscript 2 and check if it equals c superscript 2. If the condition is satisfied, we count that triple. This method is simple to implement, but it requires 3 nested loops, resulting in a time complexity of O, n superscript 3. While it works for small values of n, the cubic growth in iterations makes it inefficient as n increases. This limitation is the main drawback of the brute force approach, and it motivates us to explore more efficient strategies. To improve upon the brute force approach, we can optimize the process by reducing the number of iterations. One key insight is that in any valid triple, c is the largest value. This allows us to iterate over c separately and avoid looping over all possible values of a, b, and c. Instead, we focus on finding valid pairs, a, b, for each c. Specifically, for each value of c from 1 to n, we iterate over potential values of a from 1 to c1. For each a, we compute b superscript 2 as c superscript 2 a superscript 2 and determine if b is a valid integer within the range, 1 to n. Additionally, by only considering pairs where a less than or equal to b, we eliminate duplicate calculations. This optimized approach reduces the time complexity to O, n superscript 2, as the outer loop runs O, n, times and the inner loop handles the remaining iterations more efficiently. This method is much faster than the brute force approach and better suited for the given constraints. When comparing strategies, we see clear trade-offs. The brute force approach is conceptually simple and easy to implement, but its O, n superscript 3, time complexity makes it impractical for larger values of n. On the other hand, the optimized approach achieves a significant performance boost by leveraging the properties of Pythagorean triples, reducing the complexity to O, n superscript 2. This balance of simplicity and efficiency makes it ideal for this problem. An alternative method involves pre-computing all possible squares and storing them in a hash set for constant time lookups. While this could work for larger constraints, it increases space complexity and isn't necessary for n less than or equal to 250. Ultimately, the optimized approach is the chosen strategy because it avoids unnecessary computations, scales well within the problem's limits, and is straightforward to implement. In this problem, we aim to count all squaresome triples, which are sets of three positive integers, a, b, c, such that a squared plus b squared equals c squared, and each of these integers lies between 1 and n inclusive. For example, a triple like 3, 4, 5 is valid because 3 squared plus 4 squared equals 5 squared. The constraint n less than or equal to 250 allows us to explore different approaches, including a brute force solution. To start, we need to fully understand the constraints and the problem scope. The input is a single integer n, which defines the range for a, b, and c. Our goal is to output the count of all valid triples that satisfy the equation. A key insight here is that c must be the largest number in the triple, as it represents the hypotenuse in the Pythagorean relationship. With this in mind, we can proceed to outline a brute force approach for solving the problem. This method involves iterating through all possible combinations of a, b, and c using three nested loops and checking if the equation holds true for each combination. Although this approach is computationally expensive, it provides a clear and straightforward way to solve the problem within the given constraints. To implement the brute force approach, we structure it using three nested loops. First, we use an outer loop to iterate through all possible values of c, from 1 to n. Since c represents the largest number in the triple, this ensures we don't miss any valid combinations. Next, we use a middle loop to iterate through all potential values of a, ranging from 1 to c. This ordering ensures that a stays less than or equal to c, which simplifies our search and adheres to the constraints. Finally, we use an inner loop to iterate through values of b, starting from a and going up to c. By starting b from a, we avoid duplicates like 3, 4, and 4, 3, since these are considered the same triple. For each combination of a, b, and c, we check if the condition a squared plus b squared equals c squared is satisfied. If it is, we increment a counter to keep track of the valid triples we've found. Once all the loops are complete, we return the counter as the result. This method, while simple, exhaustively checks every possible combination within the range and guarantees correctness. Completing the implementation, the function now simply returns the counter, which represents the total number of valid squaresome triples. While the brute force approach is straightforward, there are key insights we can use to optimize it further. One optimization involves reducing the range of our loops. Since it is less than or equal to b and both are less than or equal to c, we only need to consider half the possible pairs of a and b, avoiding redundant calculations. Another optimization leverages the symmetry in the equation a squared plus b squared equals c squared. By limiting b to a range from a to c, we effectively reduce the number of iterations without missing any valid combinations. Additionally, we can pre-compute the squares of numbers from 1 to n and store them in an array. This avoids recalculating squares repeatedly during the condition checks, which can save computation time in scenarios with larger values of n. These optimizations enhance efficiency while maintaining the correctness of our brute force solution. To efficiently track the number of valid triples, we use a simple counter variable. This lightweight data structure is sufficient because the output of the problem is a single integer, which represents the count of all valid triples. However, to further optimize the algorithm, we can introduce an optional array to pre-compute squares. This array stores the values of I squared for all I in the range from 1 to n. By referencing pre-computed values during the condition checks, we reduce the computational overhead of squaring numbers repeatedly. These small adjustments can make a noticeable difference in larger cases where the number of iterations grows significantly. When analyzing the algorithm, we see that the time complexity is dominated by the three nested loops, resulting in a worst-case complexity of O, n cubed. On the other hand, the space complexity is minimal, remaining at O, 1, if we do not pre-compute squares and increasing to O, n, if we use the optional array for optimization. These trade-offs between time and space efficiency are worth considering, depending on the specific constraints of the input. When testing the algorithm, it is important to consider edge cases to ensure robustness. For small inputs like n equals 1 or 2, there are no valid triples, so the function should return 0. The algorithm also needs to handle equality cases correctly, such as when A equals B or A equals C, ensuring the condition is still verified properly. For larger inputs, such as n equals 250, the algorithm must efficiently handle up to 250 cubed iterations. While this is computationally feasible within the given constraints, leveraging optimizations like symmetry and pre-computing squares can significantly reduce runtime. By addressing these edge cases and optimizing where possible, we can ensure the solution is both correct and efficient across all valid input ranges. This solution defines a class solution containing the method count triples, which computes the number of squaresome triples for integers between 1 and n. The function uses a nested loop structure to iterate over possible values of a and b. For each pair, a, b, it calculates c underscore squared is the sum of a caret 2 plus b caret 2 and determines if c underscore squared is a perfect square by taking its square root and squaring it again to compare with the original value. If c is a valid integer and lies within the range 1, n, the triple a, b, c is counted. To avoid double counting, the loop for b starts from the current value of a. Additionally, when a is not equal to b, both a, b, c, and b, a, c are valid, so the count is increment by 2. When a equals b, the count is increment by 1. This ensures all valid triples are counted correctly while maintaining efficiency. The function ultimately returns the total count of such triples. This is the Java implementation of LeetCode problem number 1925, count squaresome triples. The logic mirrors the Python solution, where we iterate over all possible pairs of integers, a, b, calculate c, and check if the equation a squared plus b squared equals c squared holds true. Key differences include type declarations, the use of Java's math.sqrt method for square root computation, and Java-specific syntax for loops and conditionals. In this problem, we are tasked with finding all unique triplets \a, b, c such that a squared plus b squared equals c caret 2 \. These triplets are known as Pythagorean triples, and the integers \a, b, c must be within the range \1, n, where n is the input. The approach we'll use involves iterating through all possible \a, b, pairs, calculating c as the square root of a squared plus b caret 2 and checking if c is both an integer and within the valid range. To illustrate, let's start with an example where n equals 5 \. Initially, we set count equals 0 to keep track of the number of valid triples we find. Our goal is to increment this count whenever we identify a valid triplet a, b, c We begin iterating with a equals 1 \. For each a we start b at a to ensure we don't double count pairs like a, b, and b, a. When equals 1 and b equals 1 we calculate c squared equals 1 squared plus 1 squared equals 2 and c equals sqrt 2 equals 1.41 Since c is not an integer, this combination is skipped. Next, with b equals 2 c squared equals 1 squared plus 2 squared equals 5 and c equals sqrt 5 equals 2.23 Again, c isn't an integer, so we skip this too. We continue this process for b equals 3, 4, 5 but none of these yield a valid c Now, we move to a equals 2 When b equals 2 c squared equals 2 squared plus 2 squared equals 8 and c equals sqrt 8 equals 2.83 which is not an integer. Similarly, for b equals 3, 4, 5 no valid c is found. Finally, with equals 3 we calculate b equals 4 where c squared equals 3 squared plus 4 squared equals 25 and c equals sqrt 25 equals 5 Here, c equals 5 is an integer and within range, so we increment count by 2 to account for the valid triplets 3, 4, 5 and 4, 3, 5, backslash. After completing the iteration for backslash n equals 5 backslash, the total backslash count backslash of valid triplets is 2. Now, let's consider another example with backslash n equals 10 backslash. Once again, we initialize backslash count equals 0 backslash and iterate through all potential backslash a, b backslash pairs. For backslash a equals 3 backslash and backslash b equals 4 backslash, we find that backslash c equals 5 backslash, which is valid, so we add 2 to backslash count backslash. Similarly, for backslash a equals 6 backslash and backslash b equals 8 backslash c equals 10 backslash is valid. We add another 2 to backslash count backslash, bringing the total to 4. At the end of the iteration, the total count of valid triplets for backslash n equals 10 backslash is 4. There are a few key observations that make this algorithm efficient. First, the inner loop starts at backslash b equals a backslash to avoid duplicate pairs backslash a b backslash and backslash b a backslash. Second, we ensure backslash c caret 2 backslash is a perfect square and that backslash c backslash is within the range backslash 1 n backslash. Third, when backslash a backslash nec b backslash, we count both backslash a b c backslash and backslash b a c backslash as they represent distinct permutations. By skipping unnecessary calculations, the algorithm efficiently handles small values of backslash n backslash. For example, with backslash n equals 15 backslash, we find 2 additional valid triplets backslash a equals 5, b equals 12, c equals 13 backslash and backslash a equals 9, b equals 12, c equals 15 backslash, each contributing 2 to the count. This brings the final total to 8. The solution systematically identifies all valid combinations while adhering to the constraints of the problem. Here, we analyze the time complexity of the code. The algorithm uses 3 nested operations to count the number of square-sum triples. The outer loop iterates over all possible values of a from 1 to n, contributing n iterations. Within this loop, there is an inner loop that iterates over b, starting from a to avoid double counting pairs like a, b, and b, a. On average, the inner loop runs approximately n a plus 1 times for each value of a, and this number decreases as it increases. When we combine all iterations of b across the range of a, this contributes n squared / 2 iterations overall. Finally, for each pair of a and b, the code computes c underscore squared as a squared plus b squared, then checks if the square root of c underscore squared is an integer and satisfies c equals n. These operations, involving square root extraction and comparison, take constant time, or O1, for each iteration. Together, these steps form the building blocks of the algorithm's time complexity. To calculate the total time complexity, we combine the contributions from all parts of the code. The outer loop runs n times. For each value of a, the inner loop runs n iterations, which leads to a total of n squared for the nested loops. Additionally, the constant time operations performed for each pair of a and b add 1 per iteration, but this does not affect the overall growth rate. As a result, the total time complexity of the algorithm is n squared. Moreover, since the number of iterations is entirely determined by the range of a, b, and c, and does not depend on specific input values, the time complexity remains n squared in the best, average, and worst cases. This ensures consistent performance across all scenarios. Now let's discuss space complexity. The algorithm primarily uses a few scalar variables, such as count, a, b, c underscore squared, and c, to keep track of calculations. Each of these variables requires a constant amount of memory, or O1. Additionally, the algorithm does not use any auxiliary data structures like arrays, dictionaries, or lists. All computations are performed directly using the loop variables and intermediate calculations, which means no extra memory is consumed beyond the required scalars. Therefore, the total space complexity of the algorithm is O1, making it highly efficient in terms of memory usage. Let's compare this solution to a brute force approach. A naive method would involve iterating over all possible triplets, a, b, c, where 1 equals a, b, c equals n, and checking if a squared plus b squared equals c squared. This would require 3 nested loops, resulting in a time complexity of O, n cubed. The given solution improves on this by restricting b to start from a, which avoids redundant pairs, and by deriving c as the square root of a squared plus b squared instead of iterating through all possible values of c. These optimizations reduce the time complexity to O, n squared, which is a significant improvement over O, n cubed. Mathematically, the total iterations are determined by summing the inner loop runs over all values of a. This sum is n plus n1 plus n2, and so on, which equals n asterisk n plus 1/2, simplifying to O, n squared. Since no additional space is used beyond the loop variables, the space complexity remains O1, making this approach both time and space efficient. When solving this problem, there are several common mistakes to watch out for. First, it's important to handle duplicate pairs correctly. For instance, if you find the triple 3, 4, 5, you must also consider 4, 3, 5 as a valid but distinct solution. A good way to address this is by explicitly testing all permutations or ensuring both cases, A equals B and B equals A, are covered. Another common pitfall is setting inefficient looping bounds. Remember that while A and B range between 1 and n, the actual constraint is that the hypotenuse, C, must satisfy 1 equals C equals n. Keeping loops within these bounds will prevent redundant calculations and improve runtime. Lastly, don't overlook the need to verify that C is an integer. Simply computing C as the square root of a superscript 2 plus B superscript 2 isn't enough. You also need to check that C superscript 2 equals a superscript 2 plus B superscript 2 to ensure it forms a valid Pythagorean triple. Now, another common mistake involves redundant calculations. If you repeatedly compute a superscript 2 plus B superscript 2 inside nested loops, you'll waste time recalculating the same values. Instead, pre-computing the squares for all integers from 1 to n and storing them allows for quick lookups, significantly speeding up the process. Also, symmetry in the pairs A, B can lead to double counting. For example, swapping A and B produces the same result, so there's no need to count both 3, 4, and 4, 3. You can avoid this by restricting your checks to cases where it is less than or equal to B. This symmetry optimization not only simplifies the logic but also makes the solution more efficient. In interviews, this problem often tests your ability to optimize brute force solutions using mathematical properties and efficient techniques. The key idea revolves around generating Pythagorean triples while minimizing unnecessary computations. For example, pre-computing squares and eliminating redundant checks can drastically improve runtime. Interviewers may also assess whether you can leverage constraints, such as the fact that C must be less than or equal to n, to minimize the number of nested loops. Be ready to discuss edge cases, like when n equals 1, where there are no valid triples, or when n is very large, like 250, where the solution space is much bigger. A common follow-up question might involve scaling the solution for larger constraints, such as n up to 10,000. Here, you'll need to weigh time-space trade-offs, for instance, using extra memory for pre-computed values versus recomputing them on the fly. Additionally, related problems like sum of square numbers or valid triangle number can help reinforce similar mathematical and optimization concepts. Finally, let's discuss some alternative approaches. The brute force method iterates over all combinations of A, B, and C to check if a superscript 2 plus B superscript 2 equals C superscript 2. While simple to implement, it has a time complexity of O, n superscript 3, and becomes impractical for larger values of n. A more optimized brute force approach reduces this to O, n superscript 2, by iterating over pairs of A and B, computing C as the square root of a superscript 2 plus B superscript 2, and verifying its validity. Pre-computing squares further improves this method's efficiency. Another approach involves hashing. By pre-computing all squares up to n superscript 2 and storing them in a hash set, you can directly check if C superscript 2 exists for a given pair, A, B. This reduces lookup time but requires additional memory. Lastly, symmetry optimization ensures you only compute pairs where A less than or equal to B, effectively cutting the runtime in half without missing any valid solutions. Each of these strategies offers trade-offs between simplicity, runtime, and memory usage, so choose the one that best fits the constraints of the problem or interview. Great job! We've successfully solved LeetCode problem number 1925, count square some triples. We reviewed the problem, discussed the approach, and analyzed the complexities. Don't forget to practice similar problems to strengthen your skills. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!